everyone, welcome to the B.Pharm special program where we guide you to study better and in smart way. This is Swapnil Patil going to take one of the most interesting and learning topic of the B.Pharm third semester on the important unit course dispersion, which is interesting unit of the subject physical pharmaceutics. Are you ready? Our topic is divided into the three modules. Module 1, that is introduction to the course dispersions and suspension. Module 2, that is interfacial properties of suspended particles. Module 3, that is settling in a suspensions. Let's start with the general introduction of the course dispersions and suspension. Dispersion. Dispersion, what is meant by dispersions? You all know about the course dispersion, that is it is heterogeneous system in which one substance, the dispersed phase, is distributed in a discrete units throughout the second substance, that is continuous phase. Each phase can exist in solid, liquid and gaseous state. The table in front of you, which is showing that classification of dispersed system is based on the particle size. The classification of dispersed systems based on the particle size is divided into the three types: the molecular dispersion, colloidal dispersions and coarse dispersions. Basic difference between those size is like molecular dispersions, which is less than 1 nanometer, for example aqueous solution of salt. Colloidal dispersion, which is in a range of 1 nanometer to the 0.5 mm, example milk, that is emulsion of the fat and some other substances in the water. Second example, that is the natural polymers. The coarse dispersions, which is greater than 0.5 micrometer, example best way, suspension and emulsions. Now the basic topic is suspension. What is meant by suspension? Pharmaceutical suspensions are the uniform dispersions of the solid drug particles in the vehicle in which the drug has minimum solubility. That is, it contains the two phases, the internal phase, which is consisting of insoluble solid particles having the range size 0.5 to 5 microns, which is maintained uniformly throughout the suspending vehicle with the aid of single or combined suspending agent, combination of suspending agent. The external phase, that is suspending medium, is generally aqueous in some instances, or maybe it may be oily liquid for the non-oral use, that is for the topical preparation. Particle sizes of the drugs may vary from one formulation to the another formulation depending on the physicochemical characteristics of the drugs and the rheological properties of the formulations. The classification of pharmaceutical suspensions are mainly classes, that is based on general classes, mainly which includes the oral suspension, externally applied suspensions and parenteral suspensions. Second class is based on the proportion of solid particles. What might be the percentage of solid particles it contains? It contains dilute suspensions, which is of 2 to 10% weight by volume of solid, or concentrated suspensions, which contains the 50% weight by volume of solids. The based on electrokinetic nature of the solid particles, it's divided into the flocculated suspension or deflocculated suspension. Based on the size of the solid particles, it might be the colloidal one, that is less than 1 micron, coarse suspension, that is greater than 1 micron, and nano suspensions, that is around 10 nanogram. Now you understand the classifications. On the basis of classifications, you got the terminology behind what type of suspension are there in a market or what type of suspensions natures are there. But what are the reasons, basic reasons behind the formulation of pharmaceutical suspensions? That should known to you, because that is the main. What are the basic reasons? Then the reasons is first, insoluble nature of drug in the delivery vehicle. That is the main reason. And the second most reason is the enhancement of the stability of the drug candidate. Another important aspect, that is a masking of bitter test of the drug particle. Also to achieve control or sustained drug release profile for the drug candidate, which is of what? Shorter half-life. Now we will go to the formulation details of suspension. What are the formulation ingredients in the suspension? The main formulation ingredients are drug candidate and excipients. A drug candidate is insoluble in a vehicle. Mainly the suspending agents which are added are acacia, carboxymethyl cellulose, sodium, microcrystalline cellulose with a carboxymethyl cellulose, povidone, polyethylene glycol, polypropylene, glycol alginate, then tragacanth, xanthan gum. Wetting agents contains polysorbate 80, acacia, tragacanth, alginate, gorgum, pectin, gelatin, B.Gum, methyl cellulose, and many more, that is bentonite. Preservative, yes, preservative is very important in formulation aspects of suspension which prevents from the microorganisms, that is preservatives contains benzalkonium chloride, benzoic acid, propylene glycol, cetrimide, chlorobutanol, disodium EDTA, antioxidant. These are also important in order to reduce the oxidation. Ascorbic acid, tocopherols, butylated hydroxyanisole, butylated hydroxytoluene, sodium bisulfate. Sweeteners, that includes the sucrose, mannitol, dextrose, aspartame, sodium saccharin. Buffers, which includes citric acid, is the most preferable used to stabilize the pH of suspensions between, that is of percentage 3.5% to 5%. Acetates in a percentage of 1 to 2%, citrates 1 to 5%, and phosphates which are in 0.8 to 2%. Flavoring agents, that is raspberry, pineapple flavor or bubblegum flavor. Coloring agents, that is white titanium dioxide, blue brilliant blue, indigo carmine, indigo, red amaranth, carmine, yellow tartarazine, sunset yellow. Vehicles, that might be the aqueous one, that might be the non-aqueous one. Aqueous one, that is distilled water, or if it is a non-aqueous one, that is used for the topical application. Now let's move to the examples of pharmaceutical suspensions. Antacids oral suspensions, dry powders for the oral suspensions, that might include the antibiotics, analgesic oral suspensions, anthelmintic oral suspensions, antifungal oral suspensions. Now you are having a clear crystalline way, that is what is the suspension, what are the types of suspensions. Now we will move for advantages and disadvantages. Dear friends, these are the aspects which are very essential in order to make understanding of particular drug delivery system or dosage form. What are the advantages of suspension? Let's move. Advantages include suspensions can improve the chemical stability of certain drugs. For example, procaine penicillin G. Drugs in suspension exhibits higher rate of bioavailability than any other dosage form, which is like in a below mentioned order, that is solutions are having a more bioavailability than the suspension. Suspensions are having the more bioavailability than the capsule, and capsules having the more bioavailability than the tablet, than the coated tablet. The duration and onset of actions can be controlled, that is protamide zinc insulin suspension is the best example. Suspensions also have many more advantages regarding test masking. Yes, the bitter test can be masked very well by the suspensions, example chloramphenicol, for which the bitter test masking suspensions can be formulated. The disadvantage. Each and every system which is having the advantages, there might be the disadvantages. And the disadvantages of the suspensions is mainly in a critical area of physical stability, sedimentation and compaction can causes the problem. It is bulky, sufficient care must be taken during the handling and transport. It is difficult to formulate, that is the main disadvantage. Some difficulty is there. Dose cannot be achieved unless suspensions are packed in unit dosage form. Now friends, we will move to the second most important point, that is interfacial properties of suspended particles. In pharmaceutical suspensions, the solid phase remains as a finely divided particles in the dispersion medium. Therefore, large amount of interface is involved in the formation, which in turn affects the stability of suspension preparation. The interfacial properties therefore play a vital role in modifying the physical characteristics of the dispersion. The two most important interfacial properties includes surface free energy and surface potential due to the surface charge. Now we will look into those interfacial properties one by one in a details, because those are very critical and those are very essential in a suspension formulation. Surface free energy, that is the most important interfacial property. A large surface area offered by the finely divided solid material is typically associated with a large amount of free energy on the surface. The relation between the surface free energy and the surface area can be expressed by equation delta G is equal to gamma into delta A, where the delta Eg is increase in surface free energy, delta A is increase in surface area, and gamma is interfacial tension between the solid particles and the dispersion medium. The smaller is the delta G, the more thermodynamically stable is the suspension. Therefore, a system with a very fine particles is thermodynamically unstable because of high total surface area. Thus, system tends to agglomerate in order to reduce surface area and thereby the excess free energy. Now, you are looking towards that equation delta G is equal to gamma into delta A. The Gibbs free energy is the highest at the interface, and each and every system which is having a high energy tends to reduce that energy, and if it is reducing the energy, then that is going to be stabilize itself. That indicates it going to be thermodynamically stable. And the formulator is main, which is to identify that at the interface there should be an highest interfacial energy. That means particle size should get reduced in order to make the perfect formulation. Suspension, that is the same one. The concept is the reduction in interfacial tension, making the system more stable. That is formulator mainly having the job in order to retard the rate of conversion of system towards thermodynamically stable. Thermodynamically stable system will create kinetically unstable, and our pharmaceutical formulation should be kinetically stable and thermodynamically unstable. Mark my words, our system should be thermodynamically stable or kinetically stable, that is kinetically stable and thermodynamically unstable. Now, the second most important property is the surface potential. What is the surface potential? That is due to the surface charge. And how it is originated? That is originated by many way. The stability of lyophobic colloidal systems can be generally explained on the basis of presence or absence of surface potential. This theory can also be extended to the suspension systems. Surface potential exists when dispersed solid particles in suspension possesses charge in relation to the surrounding liquid medium. Solid particles may become charged through different ways. If the suspension contains electrolyte, selective adsorption of particular ionic species by the solid particles is possibility. This will lead to the formation of charged particles. For example, let's take an example, the surface active agents which are already adsorbed at the solid liquid interface may ionize to give the particles positive or negative charge. For best example, sodium dodecyl sulfate, for example, which is having that anionic charge in aqueous medium. And second way is solid particles can also be charged by the ionization of functional groups of the particles. In this case, the total charge is the function of pH of the surrounding vehicle. For example, peptide and protein molecules containing ionizable groups, as you know all, COH and NH2 groups is there, which is mainly negatively charged, and in case of peptide and proteins, dispersed particles of these type of molecules will ionize. The sign and magnitude of ionization mostly depends on the pH of the surrounding vehicle. So that is the main again why the buffers are added into the suspensions. Now you get clear cut link between why buffering agents are added in your suspension agents to maintain the pH. And why the pH is very critical, which is by citric acid. Now the second most important aspects regarding the suspension, as like interfacial properties, the main origin and theory behind the suspension, that is electrical double layer theory. When the dispersed particles are in contact with an aqueous solution of an electrolyte, the particles may selectively adsorb one charge species. If the adsorbed species is an anion, the particles will overall get negatively charged. The ions that gives the particles its charge, anions in these cases, are called as potential determining ions. As you clearly look into the diagram, the diagram indicates what? The central part, that is solid phase, solid layer, which is of negatively charged. The particles having the anions, that is negatively charged, which are at the central part, that is potential determining ions. Remaining ionic species in the solution are the rest of anions and the total number of cations added. This means there will be excess cations than the anions in the dispersion medium. The cations having the charge opposite to that of potential determining ions are known as counter ions. They are attached to the negatively charged surface by the electric forces. Counter ions also repel to each other by some forces of repulsion. These electrical forces and thermal motion keeps the equal distribution of all ions in the solution. It results in equilibrium conditions where some of the excess cations approach the surface and the rest of cations will be distributed in decreasing the amount as one moves away from the charged surface. That is known as electrical double layer, which is mainly at the solid liquid medium interface in the dispersion system. The part of the solvent immediately surrounding the particles will almost entirely comprise of the counter ions. This part of the solvent along with these counter ions is tightly bound to the particle surface is known as turn layer. Now in a second image you clearly got the theme where what are the turn layer, what is diffuse layer, what is electrical neutral layer. As in a circular diagram, you clearly indicates or you clearly got the concept what might be the particles distribution or surface charge distribution in the figure. Now we will look in a deep way, in a deeper sense behind the terminology of formulation of suspension. The deep sense of the electrical double layer now clear cutly in this planar diagram, in which three different layers are there. The layer which is A to A dash is mainly due to the potential determining ions, which might be the positive one or which might be the negative one. If A to A dash is the positively charged, then the counter ions will attack on that layer and it forms the second layer, which is known as tightly bound layer, which is towards this first layer A to A dash. The second layer is B to B dash, which is known as tightly bound layer, and third layer is a C to C dash, that is diffusion layer, and the D to D dash layer is known as electrically neutral region. Now you got the terminology. Potential of the solid surface A to A dash is known as Nernst potential, while potential at the stern layer, that is tightly bound layer B to B dash, is known as zeta potential. Nernst potential is the difference between actual potentials at solid surface and electrically neutral bulk, while zeta potential is difference between stern layer and electrically neutral bulk. Because stern layer is tightly bound to the solid surface, it is difficult to measure Nernst potential. Zeta potential. Zeta potential measurement is the more popular method of evaluation of dispersed system. Zeta potential has a significant effect in the formulation of stable suspension. Zeta potential governs the degree of repulsion between the adjacent and similar charge solid dispersed particles. If the zeta potential is reduced below the critical value, the force of attraction between the particles succeed the force of repulsion and the particles come together. This phenomenon is referred as a flocculation. The loosely packed particles are called as floccules. Consideration of the electrostatic repulsion and the van der Waals forces of attraction by Dirac-Wien, Landau, Verby and Overbeek DLVO theory that lead to the stability of hydrophobic suspension. It includes attraction forces arise from van der Waals forces between the particles of the same kind and repulsive forces arise from the electrical charge on the particles which is due to either ionization of the surface group or adsorption of the ions. Now in front of you the image is there. The image clearly indicates three curves are there. One curve which is divided into the three parts. The first part over the distance, that is repulsive forces and attractive forces balances each other over the distance, in which there are the three phases, that is the primary minimum, primary maximum and secondary minimum, which indicates that whenever there is a repulsive forces more, then there is a primary maximum, which is known as deflocculated system. When there is low level of attractive forces over the distance, that is known as secondary minimum, which is a flocculated system. While there is closer tight attraction, more attraction forces, more attractive forces will lead to the primary minimum, that is coagulated system. Now you got the terminology between the suspension, formulation aspects of the suspension and interfacial properties associated with the sedimented suspended particles. Now we will move towards the settling in a suspension. What is meant by settling? Settling or sedimentation is a very important issue in the suspension stability. It is a general trend to reduce the rate of settling, although as mentioned earlier, slow rate of settling in a deflocculated suspension may cause the particles to settle as compact residue at the bottom of the container. A commonly accepted theory that explains the settling kinetics in the dispersed system was proposed by Stokes equation. The Stokes equation is V is equal to d square into rho 1 minus rho 2 into G divided by 18 eta, where V is the velocity of the sedimentation, d is the diameter of the particle, G is acceleration of gravity, rho 1 is the density of the particle, rho 2 is the density of the vehicle and eta indicates viscosity of the vehicle. According to the Stokes equation, the velocity of sedimentation of the particles in the suspension can be reduced by decreasing the particle size and also by minimizing the difference between the densities of the particles and the vehicle. Since the density of the particles is the constant for the particular substance and cannot be changed, the changing of density of the vehicle close to the density of the particle would minimize the difference between the densities of the particles and the vehicle, and the density of the vehicle of the suspension can be increased by adding the following substances, either alone or in a combination, that is polyethylene glycol, polyvinyl pyrrolidone, glycerine, sorbitol and sugar. The viscosity of the vehicle also affects the velocity of sedimentation. It decreases as the viscosity of the vehicle increases. The viscosity and the density of any vehicle are related to each other. So, any attempt to change one of these parameters will also change the other one. Now let us move towards the main area of formulation of suspension, that is flocculated or deflocculated. What is meant by flocculated or deflocculated? The deflocculation of the particles is obtained when the zeta potential is higher than the critical value and the repulsive forces supersedes the attractive forces. The addition of small amount of electrolyte reduces the zeta potential. When the zeta potential goes below the critical value, the attractive forces supersedes the repulsive forces and the flocculation occurs. The following same, that is the difference between the flocculated and deflocculated, very well illustrated in the table. Let us move towards the difference between the flocculated and deflocculated suspension. Flocculated suspension and deflocculated suspension. Major difference in points, that is first point, particles forms loose aggregates and form a network like structure in case of flocculated one, while in case of deflocculated particles exist as a separate entities. In case of flocculated, the rate of sedimentation is high, the rate of sedimentation is low in case of deflocculated suspension. Sediment is rapidly formed, while in case of deflocculated suspension, sediment is slowly formed. Sediment is loosely packed and does not form hard cake in case of flocculated suspension. Sediment is very closely packed and hard cake is formed in case of non-flocculated suspension. Sediment is easy to redisperse, while in case of deflocculated, sediment is difficult to redisperse. 6th point, that is suspension is not pleasing in appearance in case of flocculated one, while in case of deflocculated, suspension is pleasing in appearance. And the last point, that is the floccules stick to the sides of the bottom, while in case of deflocculated, they do not stick to the sides of bottle. Now friends, what is the conclusion of today's session? The conclusion is suspensions. Suspensions are an important class of pharmaceutical dosage form that may be given by many routes, including oral, topical, parenteral, and also used in the eye, that is for the ophthalmic purpose. Surprisingly, large proportions of the new drug candidates that are emerging are predominantly water insoluble, and therefore they lead to the poor bioavailability problem in the solution dosage form. While in case of suspensions, viable formulations options for many drugs, particularly for the water insoluble hydrophobic drug substances, and this module has dealt in sufficient detail regarding the theoretical considerations of pharmaceutical coarse dispersions, which includes interfacial properties, electrical double layer theory, flocculated, deflocculated systems, stability considerations. In that, there is a settling, sedimentation, effect of particle size on settling of suspensions, and the rheological considerations. A thorough understanding of these aspects is important from stability point of view, as the stability of suspension system depends both on properties of dispersed solid phase and on those of vehicle. Apart from the gravitational sedimentation, the behavior of the solid may be determined by the zeta potential. Concise information on the zeta and Nernst potential is provided. Drugs from the suspension formulations typically exhibit an improved bioavailability when compared to the same drug formulated as a tablet or capsule. For example, suspensions of antacid preparations offered a more rapid onset of actions and therefore more effective formulations of suspensions than equivalent dose of the same drug in the tablet dosage form. Now friends, nanosuspensions have emerged as a promising strategy for the efficient delivery of hydrophobic drugs. Because of their versatile nature and unique advantages, rapid advances have been made in the delivery of nanosuspensions by the parenteral, peroral, ocular, pulmonary routes. Currently, efforts are being directed to the extent their applications in a site-specific drug delivery system. With all these informations, here we come to the end of topic. I will be back with one more interesting lecture in the same series of physical pharmaceutics. Till then, keep studying. Goodbye friends.